Welcome to this video from the Solutions chapter. This lesson is going to follow our previous two lessons on molarity and dilutions, and we'll focus on the other ways that we can express the concentration of a solution. So please take out your CsRT, turn to table T, grab a calculator, your writing utensil, and a notebook, and let's get ready to learn about concentration. So you guys are going to see that this video covers 5 different formulas: general solubility, percent composition, and parts per million. Stop the video right now and let's take down what the formulas actually are in your notes, and then unpause the video when you are ready. So the first formula we're going to tackle is our general solubility formula, which when we were taking notes we saw that there were 2 of those. We're going to tackle general solubility by mass before we do volume. You guys know that formula is mass of solute over mass of solvent. And a typical question might be, according to table G, what's the solubility of a saturated solution of NaCl at 90 degrees Celsius? And so let's jump right to table G. They're saying, what is that ratio? What is that solubility value? And what we need to do is go into table G and tease out the information to tell us what the mass of solute is and the mass of solvent. Well, let's hit mass of solute first. You guys know table G is the solubility curve table, and each one of these lines represent the saturation point for any one of these salts at a given temperature. Since we're talking about NaCl at 90 degrees, we're going to plot out how much sodium chloride it takes to saturate the solution, and we can see it takes 40 grams of sodium chloride. But that saturates 100 grams of water. So that's where we get this denominator from that's there. So the 40 goes up here, the denominator of 100 grams goes down here, and if we set up the problem, we get 40 over 100, which gives us a ratio of 0.40 grams of NaCl per 1 gram of water. Super easy. We can look at the other formula, which is now talking about general solubility in terms of grams per milliliter, the same sort of way. One thing we have to take into consideration is if we're using table G, it doesn't say anything about any volumes, but we have to remember that the density of water is 1 gram per milliliter. So at that point, if I had 100 grams of water, this 40 grams of NaCl that we plotted out before is going to be dissolved in essentially 100 milliliters of water. So when we set up the problem, it does look very similar. 40 grams of NaCl over 100 mils of water give us 0.40 grams per milliliter, and that is the general solubility. The next formula we want to talk about is percent composition. And let's start with percent composition by mass and look at a practice problem like this. It says bronze is typically made of 40 grams of copper and 10 grams of tin. So bronze is a mixture. It's a physical blending of these. It's an alloy. What is the percent comp by mass of copper in bronze? Well, to set that up, we got to think of the formula for percent comp. And we know that that's mass of part over mass of whole times 100. So let's now take that formula and decode this question. We are looking for the mass of copper, which they're telling us is 40 point, which gives us 2 significant figures. And we got to put that over the mass of the whole. Do not forget that the whole consists of the 40 grams of copper and the 10 grams of tin to give us 50 grams total. So our setup for this is going to look like 40 grams over 50 grams, and don't forget your decimals, to give us an 80% copper in bronze. So our percent by mass of copper in bronze is 80%, and it is to 2 significant figures because remember, in multiplication and division, we have to take the least. The second percent composition formula is percentage by volume. So now we're dealing with the space that something takes up, not its mass. A typical question could look like this. It says a nonpolar solvent is prepared by mixing 10 milliliters of butane with 90 milliliters of carbon tetrachloride. So nonpolar with nonpolar, like dissolves like. Hey, we make a solution. What's the percentage by volume of butane in that solution we just made? Well, we know we're looking for volume of part over volume of whole times 100. So the part we're looking for is indeed butane. And the next thing we got to do is figure out the total volume. Well, we can see that the butane is 10 milliliters and it's getting combined with 90 milliliters of carbon tetrachloride. And so that gives us 100 milliliters of total solution. So part over whole times 100. If I take 10 over 100 and multiply it by the 100, that gives me approximately 10% butane by volume. Do not forget it is to two significant figures here, so make sure you have the dot here to render these digits significant. The last formula I want to go through is parts per million, and it is recognizable if you've done any reading on pollutants. Parts per million tends to be used for small concentrations, and when we're dealing with pollutants in water or in air, we see parts per million, parts per trillion, parts per billion, any of those numbers. But it doesn't have to be used strictly for pollutants. It could be anything. Like, for instance, here we're making seltzer. It says how many parts per million of carbon dioxide are there in a soda containing 0.0152 grams of CO2 in 2,000 grams of water. So, if you got a soda stream, you could totally appreciate this. The formula we're going to use is exactly as you copied down before. Parts per million is mass of solute over mass of solution. But unlike the last two that we did, we are multiplying by 10 to the 6, which is 1 million. So decoding this question, we're trying to figure out how much CO2 there is, right? So we are now looking for CO2 as our solute, and we have to figure out what the total solution mass is. We can see that it's 2,000 grams of water, and we can see that it's 0.0152 grams of CO2. So we have to add those together. Mind your sig figs. When we do that, our mass of the total solution actually goes out to the 10th, the 100th, the 1,000th, the 10,000th place. Not that it'll make a difference in the end. When we actually do the math, we have 3 sig figs up here. We have 1, 2, 3, 4, 5, 6, 7, 8 down here. We got to go to the fewest number because it's multiplication and division, and that gets us 7.60 parts per million. One small side note, put this in your notes. If this was parts per billion, it would be 10 to the 9. If it would be parts per trillion, it would be times 10 to the 12. So you may see that somewhere along the way. Don't be surprised. All right, now that we've nailed all this down, open up your plan sheet and let's work on worksheet number 8, which is other solubility calculations. There's going to be a little bit of this and a little bit of that, starting off with a spot for you to put your formulas. So that's about it for me, everybody out there in YouTube land. I will see you all soon. Hope everybody had a good lesson, and I look forward to seeing you in the burning questions segment tomorrow in class. Peace out.
That's all, folks.